Welcome to the deep dive. Today we're really getting into the hidden bits of telecommunication networks, all that specialized gear that moves your data around the world. You sent over some great material. Our mission today is to unpack, well, two main parts: the on-ramp where traffic first gets in, and then the superhighway that carries it long distances. We're going to see what's really going on under the surface.
Yeah, and what's really interesting is how these different layers, the access part and the transport part, they use very specific equipment. Understanding what each bit does is pretty key to seeing how it all works so smoothly and reliably, too.
Okay, let's start right at the edge then. The network's on-ramp. That's the access layer, right? This is where everything first connects, like cell towers, businesses, even our home internet.
Exactly. That's the first point of contact. And the devices there, often called cell site routers or CSRs, sometimes multi-service access routers. Their main job is just gathering up all those different types of traffic, getting it ready for the next step.
Okay, so gathering, you mentioned diverse traffic. What are we really talking about there? Like mobile backhaul, all that 4G, 5G stuff must be huge.
Oh, absolutely. Mobile backhaul is a massive part of it. All the data, the voice calls, the signaling that makes your phone work. But another really critical thing is their multi-service capability. They don't just handle the modern stuff like packet-based Ethernet. They can also deal with older TDM services.
TDM, like the older phone lines, E1s and T1s.
Yeah, exactly those. Think legacy business lines.
Yeah.
Being able to handle both, let's network operators evolve their network gradually. They don't have to rip everything out at once.
That makes sense. Now, you also mentioned something, timing, clock synchronization. Why is that so incredibly important here, especially for mobile?
Timing is absolutely crucial. Non-negotiable, really, for mobile tech. Think about coordinating when your call gets handed off between cell towers as you move, or just making 4G and 5G radio signals work efficiently together. You need incredibly precise, stable timing for that.
Wow, okay. So how do these routers deliver that kind of precision?
They use specific protocols. One is synchronous Ethernet, or SYNC-E. It cleverly embeds timing right into the Ethernet signal itself. And then there's IEEE 1588 version 2, usually called PTP, Precision Time Protocol, that uses really precise messages passed between devices to get their clocks aligned, often down to the nanosecond level. It's amazing stuff.
Nanoseconds. So these access routers aren't simple boxes at all. They're aggregating, handling old and new tech, providing super precise timing, and they've got routing smarts too, right? IP, MPLS. Plus, they must be tough if they're out near cell sites.
Exactly right. They often live in harsh spots like outdoor street cabinets exposed to weather. So yeah, ruggedness is key. So this first mile gear, it's versatile, it's tough, and critically, it's a master of timing. Without that precision, honestly, mobile networks just wouldn't work reliably.
Okay, so traffic's collected, times perfectly. Now it needs to travel, right? Hit that superhighway. That's the transport layer's job. Moving huge amounts of data, fast and reliably across cities, maybe countries.
That's it. And this layer mainly uses what's called Packet Transport Network Equipment, or PTN. Think of it as the modern version of older transport networks like SDH or SONET, but rebuilt from the ground up for today's world, which is mostly packet data, Ethernet, IP. These are the really high-speed data highways.
High speed, high capacity, just how fast are we talking?
You're talking massive volumes.
Yeah.
These things are built around seriously fast optical interfaces. Under 100 gigabits per second is common now, even 400G. They link up the major network hubs. And for the operators running these networks, reliability is everything. Carrier-grade reliability. PTN is designed for what they call 5 nines availability.
5 nines, 99.999% uptime. That sounds intense. How do they even achieve that?
Well, the key technology is MPLS-TP. It provides really robust, predictable protection switching. So imagine someone digs through a fiber optic cable by accident. Happens all the time. The network automatically spots that break and reroutes all the traffic onto a backup path. And it does this in less than 50 milliseconds.
Less than 50 milliseconds. That's faster than you can blink. You probably wouldn't even notice.
Exactly. Often you won't notice any disruption at all. Your connection just keeps working. It's designed for that kind of resilience.
Incredible. And beyond just keeping the connection alive, can they guarantee quality, like for businesses that need really stable connections?
Precisely. That's another big strength of PPN. It's great at creating these dedicated tunnels across the network. These tunnels come with strict guarantees, service level agreements or SLAs. They guarantee specific bandwidth, really low delay or latency, and minimal variation in that delay, which we call jitter.
And that's critical for things like, what, financial trading? Or maybe remote medical procedures.
Absolutely. High priority mobile backhaul, crucial enterprise services, real-time applications.
Mm.
Yeah, things where you need basically flawless performance. It provides a level of predictable quality that's hard to get otherwise.
Okay, this is a huge, complex system. Managing it all must be quite the challenge, right?
It definitely is, which is why PTN includes a really powerful set of tools for operations, administration, and maintenance OAM. These OAM tools make it much easier for operators to set up new services, keep an eye on the network's health, find faults quickly if something does go wrong, and measure performance. It
Mhm.
actually makes managing these large transport networks simpler in many ways than trying to do the same with standard IP routers.
So let's bring this back to you listening. We've seen how your data gets onto the network's on-ramp, these smart, tough, timing-obsessed access routers,
Yeah.
and then how it blasts across the superhighway using these high-speed, ultra-reliable packet transport nodes. These aren't just generic boxes, they're highly specialized pieces of a giant interconnected system.
Yeah, and stepping back, you really see the engineering marvel behind, well, everything you do online. Every call, every video you stream, every quick search. Each layer, access, and transport has its own critical job designed specifically for the demands placed on it. It's quite something.
It really is amazing how these different parts doing different things just work together so seamlessly behind the scenes. So, for you, our listener, maybe a final thought. Next time you're, I don't know, streaming a 4K movie without a glitch or having a perfectly clear video call, just take a second to think about this invisible, incredibly complex dance happening with all the specialized equipment and maybe wonder what's the next big leap these engineers are cooking up in their labs to make it all even faster, even more reliable? What's coming next?